Okay, so today we'll start with isoparametric formulation and numerical integration. And I know these are words that are strange to you right now, but you'll follow it as we move along today, okay? So in the previous lecture, what we discussed was how to use finite elements actually to solve a 1D elastic bar problem. And I showed you how to do a thermal problem, a heat transfer problem, okay? Today, I'm going to show you some aspects that we saw last week that were not that clean. It was not very efficient. But before I go to that, let's examine the steps that it takes to implement finite elements. The first step is to derive the physics of the problem. Then you formulate the general element behavior. How you solve the partial differential equation over the domain, a simple domain, and hopefully that domain can be used repetitively. To do that, we have to derive the weak form of the partial differential equation, or ordinary differential equation. Then we approximate the function over that domain, and we will develop the element stiffness matrix and force vector. So in weak form Galerkin, we use approximation functions that satisfy the essential boundary conditions, just essential boundary conditions, and we found that the coefficients had no meaning. And so what we did is we reformulated the approximation function so that the unknowns now become the unknowns at the nodes. The nodal values are unknown. And so with that, we developed the element stiffness matrix and force vector. Then you take the structure that you're interested in, you discretize the domain into elements, and then you assemble the stiffness matrix and force vectors. You impose the boundary conditions, the loads also, and then you solve the system of equations. And then you post-process the results. Those were the steps. And I'll keep repeating this every lecture to remind you. If we recall, for our implementation for the 1D bar, weak form Galerkin, we basically start with a partial differential equation, okay? And then we multiply this by a weight function, okay? We multiply this by a weight function. This v should not be here, okay? So ignore that. But we multiply this by a weight function, v, and then we integrate this partial differential equation over the domain, okay? And then we weaken the continuity requirements, and we arrive to the weak form Galerkin. The weak form. So this is your weak form, and from here, what we did is that we plugged in the approximation to the solution, which is basically basis functions times the nodal quantities. This is your approximate solution. And the shape functions are known. You know those functions, okay? That's what we did last week. And we realized that we had to calculate du dx. And so du dx is right here. So I took the derivative of du dx here. So I get n prime, n prime, n prime. That's what you see here. Repeat it down here. And so now, I'm ready now, I'm primed, so to substitute this in to my weak form Galerkin. And so I did that. Now remember, we call this B, bold B, and the reason we do that is so we don't have to track all these matrices all the way to the end. We can just kind of save some time. So we call this B, bold. This is D, the deflections. In this case, our deflections. We call this N, bold, and that deflection D. And we just substituted that into our weak form, and we chose for the weight function V, for each of the weight function V's, for a quadratic element, how many basis functions you have? Three. Ni, Nj, and k. And each of these basis functions is related to each of the nodes, I, j, and k, right? And so we choose V to be Ni, V to be Nk, V to be Nj. And then now I have three equations, and the three unknowns for that element are ui, uj, and uk, right? Follow?
Yep.
Great. And I can put that in matrix form. I realized quickly that this B transpose right here, and that's N transpose. So that's why you see B transpose there, B, and then N transpose, and so forth. And all we had to do, we didn't have to go through this step. All I had to do probably is look at the weak form Galerkin and and replace V by N transpose. And if you did that, you can skip these steps here. And then what we did, we applied it to this problem. And I want to revisit this problem a little bit more with you again. So I took an element that was short, an element that was longer, so two elements here, quadratic, each of them, okay? And I had a node here that was quite not in the center and another node that was on the right. I did that on purpose to demonstrate something for you. And you can see the element connectivity for element 1 is 0, 1, 2, and for element 2 is 2, 3, 4. And so what we did in this example, I showed you the steps that we took. We calculated shape functions. Everybody here knows how to derive shape functions now, right? It's a very quick process, but you have to calculate them. And so we got it for the first one, and it can take some work, as you know. You know, it wasn't as simple as these are the shape functions. I had to do some work to get them. Do you agree? We had to do some work, and there were some steps involved. And we talked about those steps. We used the Kronecker delta property to figure out what the shape functions look like, and we use the partition unity property to figure out what the shape functions look like. As an example, for Ni, this shape function belongs to this node, okay? So we must have this to be 0 at this node and that node, and to do that, we came up with what these need to be, okay? These polynomials need to be, so that when I substitute these values here, it goes to 0. But then yet, we came with a coefficient to this shape function so that when I substitute x equals 0 in here, so say I put x equals 0, I get L squared. So then I have to put an L squared, so I get 1 as a ratio. So we talked about that process. And then very quickly, you realize, okay, I have to calculate it for element 1, but I'm not done yet. I also have to do it for element 2. So for element 1, this is what I got for shape function. For element 2, this is what I got for shape functions. And they look different, as you can see here. So just imagine if I have 1,000,000 elements in my airplane. I have 1,000,000 shape functions I have to come up with, because maybe every single element may not look the same, may be different. And the location could be different. You agree? They could all look different. A lot of work. If you remember, we also had to calculate B, the derivative of these shape functions. If you remember, that was part of the operations. Well, I had to do it for element 1, calculate that derivative, and also I had to integrate it from 0 to L. But for element 2, I had to recalculate that derivative. Because these ends are different for element 2. So I have to calculate these derivatives again, okay? And I have to take the integral, but the integral now is different limits also. It goes from L to 4L. Do you see what's going on here? Right? Are you seeing that for each element, I have to treat it differently? So what is the issue? In the previous example we discussed with the two elements, these shape functions, integration limits, and the derivatives of these shape functions, they change from element to element. Okay, that's not convenient. That's not very advantageous. Although we came up with something that's close to finite elements, and it is finite elements, it's not systematic enough. It's removed from the final goal. The final goal is for you to relax. Okay, that's not what we've accomplished yet. And so, well, you will never relax in this course, but you know what I mean. The idea is to make it a little bit easier for the code. You know, it would be great if my code was, when I integrated every single element, the domains, it would be great if my domain went from one number to the next one, but it would be the same for every single element. If all my elements, the integrals went from -3 to 3, that would be great. What if my shape functions were the same for all of them? What if the derivatives would be the same for all of them? I'm done. It's much easier, right? So what we'll be discussing today is an approach to doing that, okay? Because that's how finite elements is coded up, is using this technique. Okay, so actually this part blows my mind away, because you can take any shape that I have of element and make it look like a square. I can make this element that looks like a pie, like a cake piece, and turn it into a right side triangle. I can take this node, this element, which has coordinates x1 and x2, with a middle node that's not in the center, somewhere in between, and I can turn it into something that goes between -1 and 1, with a node in the center. You imagine if I can turn everything into something repeatable, and all I have to do is to solve weak form Galerkin over these elements. I don't even care how it looks right now. I want to solve this. And if I know how to solve this, maybe I can turn it into that. Okay? Everybody's following the motivation, what we're trying to accomplish? Okay. Because it'll be great if all the homework problems were squares and triangles and center node, right? But they're not, right? That homework due this Thursday probably has different element size, was it? Yeah, I did that on purpose. Because the next homework, if you want to start now, start now. The homework next Thursday is using this technique. And you will see that the shape functions are the same, the integrations limits are the same, the derivatives of the shape functions are the same for all the elements. But there's a catch. You still have to do one calculation. I'm so sorry. We'll see that. We'll look into that now. Okay? So the strategy, the solution, is to make all the elements look the same. And so we want all the elements to share the same shape functions, the same integration limits, the same derivatives of the shape functions. And our technique is to map an arbitrary shape to a standard shape. Okay? And if I can do that using this technique called isoparametric mapping, then I will have a very systematic approach, because once I have that information stored in the computer, hey, I'm going to use this element type. This element type is going to have the same shape function, derivatives, so I can actually store that information in the code and only worry about the geometry. So I'm basically decoupling the geometry from the problem. That's really what I'm doing. Do you see what I'm saying? We're decoupling the geometry out of the problem and tackling the geometry separately. To do that, let's go through this. And this can become a little bit complicated, but if you follow me, I think you'll be successful. So just pay attention to what I'm doing, and I think you'll get it. Okay? So let's look at what's going on here. I'm going to take a mapping. So let's say I have an element that goes from xi to xj. My goal is to make this element go from -1 to 1. And I'll explain later why we want to go from -1 to 1. But for now, bear in mind that our goal is to go from -1 to 1 for a linear element. I'm looking at a linear element here. And to do that, hey, why not use the shape functions that I have previously defined as the ones that are going to help me do this mapping? So I'll just use these same guys that I had defined in this coordinate system. Let's see, for example, if these shape functions actually work out. So if I use this shape function here for that node and this shape function for this node, let's see if this actually makes any sense whatsoever. So C at 1, do I get 0? So for this shape function belongs to node I. This shape function must be 0 at this node. You agree? So does it work out? If I put C1, do I get 0? Yeah, excellent. If I put C minus 1, do I get 1? Beautiful. I have a shape function that seems to work. Let's look at this one. This shape function must be 0 at this node, because this shape function belongs to this node. So if I put C equals -1, do I get 0? If I put 1, do I get 1? Because I get 1 plus 1, 2. 2 divided by 2, 1. Beautiful. Now let's see if using these shape functions, actually I can map. I can go from here to there. Okay? Let's see. If I put C equals -1, this goes to 0. You agree? That goes to 0. So I get xi. So -1, I got xi. Yeah, it does work out. This is x as a function of c. If I put c minus 1, I get xi. If I put c equals 1, which is this one here, what do I get? This goes to 0. I get 1 here and get xj. Can you see quickly how that mapped out? That's all. That's all. This mapping right here is actually working out. It's taking any element that I may have anywhere and it's put into minus 1 to 1. Anybody disagrees in that statement I made? I mean, it is really working. We just did an example here. Now the shape functions would be 1 minus c divided by 2, 1 plus c divided by 2. And guess what? Guess what I'm going to do? For my displacements, which is what I'm interested in, I'm going to interpolate them using the same shape functions here. I'm going to use these shape functions here to interpolate the displacement. So then I have ui times shape function 1 plus uj times shape function 2. That's beautiful because if I look at c minus 1, I get 2. 2 divided by 2 is 1. This is 0. So at c minus 1, I get ui, which is the value here. At c equals 1, I get this is 0. This is 1. I get uj, which is that node. So it's mapping very nice. And the shape function, guess what? These shape functions, they don't know about geometry at this point. All they know, this shape function, all this shape function knows, I go from minus 1 to 1. That's the only thing this shape function knows. What we've introduced now that provides that information is this mapping right here. This is the only thing that contains that information. And so I have decoupled it to some level. Okay? Now, I can write in matrix notation because that's what we're going to have to use over and over and over. So I'll take this shape function, put it into a matrix. So the first term is 1 minus c divided by 2, and the next term is 1 plus 2 divided by 2. And this vector is xi and xj. Okay? Similarly with the displacements, I'll put the shape function 1 and shape function 2 next to each other, call it n, and then ui and uj is your vector of displacements. Okay? Any questions on that?
Is there a reason that people prefer minus 1 to 1 instead of 0 to 1?
So the question for the video is there a reason why we're going from minus 1 to 1 and not 0 to 1? You'll understand why towards the end as I go forward. Is that okay if you wait? I want to keep you entertained. If I tell you now, then you'll leave. Let's keep you entertained. I want to keep the curiosity in there. Why minus 1 to 1? That's a great question. Why I'm doing that to you? Let's look at a quadratic element. Quadratic element is no different. For quadratic element, I'm going to use shape functions that are satisfy the Kronecker delta property and they satisfy the partition unity. And if I take a note, you know, this is incredible. This is the most incredible thing in finite elements. I have this node. It's not in the center. It's not. It's biased towards the right. You agree? This is incredible. Don't you agree? That after I put this mapping in with these shape functions, it goes from this to minus 1 to 1 with a center node at 0. Every single element. I can do that. Isn't that interesting? Okay? I can take every element, may have different size. Different size. This node could be more to the right or more to the left. I put it through this mapping, and it gives me a minus 1, 1, and a node in the center, right in the center. By doing this, I'm accomplishing a lot because I'm simplifying the problem, which is what finite elements is trying to do. Finite elements is trying to solve a very complicated or a simple differential equation, and it's trying to put it into a very simple term. Solve the system of algebraic equations and tell me what the solution is to the differential equation. It could be a heat transfer problem, magnetic problem, moisture diffusion problem, fluids problem, solid mechanics, I think is the reason you may be here. Forgot that one. More important one, right? Voltage. You tell me which problem you want to solve, and we can set it up. And I'll show you in an example little bit on. So let's see if this works, because we need to check it. And I'll walk you through this, right? So this shape function right here, let's see if I get what I need to get. So at minus 1, this node needs to map to this node. You agree? That's what we want. So if I plug in minus 1 here, you agree that these are 0? Clearly, these are 1 minus 1, 0. 1 minus, that's 0. And if I put minus 1 here, I get minus 2 times minus 1, 2 divided by 2, 1, I get xi. Works, right? Yes?
Yes.
Everybody follows. So let's look at this middle node here. This middle node here, you can really quickly see that at 0, which is this middle node, I get this to be 0, this to be 0, and the middle one gives me xk. Okay? And the last one also. The 1 actually transfers very directly to xj. So they're mapping. They're mapping exceptionally good. And the shape functions now can also be used for the displacements. Okay? I can use the same shape functions, and you'll see it's going to work out that the displacements ui, uk, and uj correspond to these displacements here. Okay? Well, the ui, uk, and uj really corresponds to the displacements here, here, and here, but since they map to this one, they also correspond to the displacements here. Everybody agrees? Yes? I'm tricking the system. Well, I didn't do this, right? It was whoever invented this technique, which is amazing. Okay. All right. I'm gonna put these shape functions in a vector of shape functions like we did before, n, and then x for the coordinates. So notice now how I'm tracking coordinates now. I wasn't quite doing that before. So I'm tracking the coordinates very separately here. Xi, xk, and xj. If you're curious about what is xi, xk, and xj is, as an example, I could have this element go from 0 to 4. Xi in this example is 4, xj is 4, and then the middle node, whatever number I chose to have it. So these are basically numbers. These are numbers. This vector here is numbers. The shape function is known. That shape function is true for everyone. Every single element in the domain that we're talking about shares the same shape functions. I don't have to calculate them again. That's excellent. I don't have to do that again. And the displacements are interpreted this way as well. And so I'll put the displacements ui, uj, and uk into this vector here, d. Okay? So that n times d gives me this multiplication right here. Okay? Any questions? Any questions? Let's go a little bit deeper here now. How do I turn something that had an integral going from xi to xj? You know, this was for the elastic bar, if you remember. Okay, I'm not going to repeat the derivation of that because that was covered previously. But that was for the linear element, if you recall. For the linear element, recall that this derivative b was basically dn dx, dj dx, and then I have b bold. I call that b bold, if you recall. And then that's the d bold there. And what I did, I substitute, what I really want to do is substitute the x as a function of c. So here, I have x as a function of c for the quadratic, and for the linear, I have x as a function of c here. Okay? What I want to do is substitute this equation into the top equation there that you saw. So my goal is to substitute x as a function of c here, and then also here, everywhere x shows up, because b has it. B has an x there. So I have to put in there x as a function of c, x as a function of c, x as a function of c. Everywhere it shows up, you have to do that transformation. Now, everybody remembers in school how to change the limits of integration? All you did was to substitute. In our case, we're doing that change in variables. That's really what we're doing. So when I substitute x as a function of c, everywhere here, now my integrals go from minus 1 to 1, minus 1 to 1. Very simply stated. But now we have to keep a track that these shape functions here now are a function of c, and this dx here is dxc. Okay? But all I've done is substitute that x is in here. Okay? And just by doing that, I have changed the limits of integration. Okay? If you go back and revisit your calculus class, that's exactly how you did it. Okay, any questions so far on what I've done? I just took the solution for the elastic bar, right? And I changed the limits of integration from minus 1 to 1 by substituting what x is in here. Okay. Now it's not very obvious what I've done so far because I haven't done very much yet. Okay. Any questions? In a question in the back here.
Why is it the integral from -1 to 1?
Why we chose the integral to go from -1 to 1? I'm trying to change any shape, any element I have, I'm trying to turn its shape to go from -1 to 1. So my domain now goes from -1 to 1, right? That's why. Okay, let's see what we're doing here. So that was x, that's n, and what I'm going to do now is calculate what this dx means. Okay, what is the dx in terms of c? That's really what I need here. So, and I also have a dx as a function of c also. To do that, you have to do chain rule differentiation, which is what you also had to do if you go back to your, when you had to change the limits of integration back in calculus. So dxc is basically a derivative of x with respect to c dc. Everybody agrees with that? Yes? Please do not be feared by this. There's nothing to fear about. All we've done is changing the integration limits. So now I have this. Now this, I'm going to call it j for now. Okay, just call it j for now. But this j is basically dx dip c. Now you agree that I know what x is a function of c? Do I know that? That's dx dip c. I can find that very easily. So I have dx dip c, so it's a derivative of c respect to that x that you see there on the left-hand side, top left-hand side. Okay, nothing to be worried about. All we've done is we want to take this derivative here, and that's what goes in here, this j there. Okay, that allows me to make this dx into j dip c. That allows me to change that to j dip c. Okay, so all I'm doing is calculating this here, this relationship, so I can substitute it into my integral. Any questions on that? Okay, now if you realize here, that's shape function 1, right? I, shape function j. So if I take the derivative, I really have this derivative. That's really what I have. That's what I'm taking, right? I can put it in matrix notation very nicely, and then I have xi, xj. I can call this b bar, just for fun. So I don't have to track that. B bar times x. Okay? X are the coordinates. So j is all these things. J is this, j is that. Okay? And I'm putting in this format because it's going to be advantageous to define this later on. You will see why. B bar. Do you agree that this does not depend from element to element? No. Every element, this calculation is the same. You agree?
Yeah.
Are you seeing where I'm going with this? I'm slowly taking my integral that went from xi to xj, slowly converting to -1 to 1. Very slowly, because I have to teach it. Otherwise, I'll go fast, right? So the first step that I'm doing is taking this dx and turning it to dip c. And for me to be able to do that, I have to do this chain rule. That's what we did there. All these steps are about that. Now, we can do the calculation. So what is the derivative of 1 minus c divided by 2? Sorry? Minus 1/2. Right? What is the derivative of this with respect to c? Plus 1/2. So xj minus xi divided by 2. You agree? So xj minus xi divided by 2. What is xj minus xi for a linear element? That's the element length. So I basically have L over 2 for that, for j. So basically all these calculations you see here give me a j equals of L divided by 2. Okay? Okay. So now I have this dx turning to j dip c. I have this dx turning to j dip c. Okay. I'm not done yet. A lot more steps to go. Okay. Now I have to deal with these b's. These b's if you recall, have this b has dn dx, but this is a problem. N is not defined as a function of x, it's defined as a function of c. You agree? So I have to do more work here. I'm not done yet. So to tackle that, b was this dn dx, dnj dx. That's what we define as b. So now I have to use chain rule again. Okay? So let's look at dn dx. dn dx, to calculate that, let's start with, we know n is a function of c. You agree? So dn dip c equals the derivative of n respect to x, x respect to c. You agree? Because this cancels out, gives you this one here. This one you know. You agree that you know this one? Do you agree that we know this one? Yes? Do you know that if I know this one and I know that one, I know this one? Well, then I know this guy here. Okay? Now you realize quickly, this is j again. That's j again. I calculated j earlier. So let's call that j. And if I solve for this here, I get dni dx equals dni c j inverse. Or 1 over j. Whatever you want to call it. 1 over j is fine with me. Okay. And now we can repeat it for the second one. Derivative of n respect to c for the second one here. Okay. Again, I see some lost faces, so I'll try to repeat. Is n as a function of x? Is n a function of x? No, it's not explicit function of x. It's only a function of c. You agree? So I cannot take this derivative that easily. I have to use chain rule. That's why we're doing chain rule. So dn dip c is really something I know. I can calculate this. But this is also equal to the derivative of n respect to x, x respect to c. This is j, the Jacobian. I'll call it Jacobian now for the first time, because I didn't want to call it anything earlier. But j, that's j. J equals the derivative of x respect to c. Now, if this is j, I can solve for this. And so now I have that equals this times j inverse. Okay? Everybody's following this. This is what's cool about this. This is b. You agree? That was b? Okay? But I found that for both of my b's, this derivative of n respect to c, j inverse. Derivative of n respect to c, j inverse. For both of them. So I can put these two guys side by side again, and I'll put a j inverse outside. What I want you to notice is that we already calculated this earlier. I did that in the previous page. This is what I had called b bar, remember? To calculate this dip x, we call that b bar. I'll let you stare at it a couple of minutes. Okay, that's b bar right there. So that's b bar then. B bar times j inverse. Now this b bar, that matrix right there is true for every single element. Every single one of them. Okay? I already know what j is. We calculated it was L over 2. So this is 2 over LE. Right? So now I've converted. If I substitute this b for b bar j inverse, I substitute that in, I'm done. I'm basically done. So I plug this for BE, plug it in there. I already have that, N transpose. Okay? I'm basically done. And then this j inverse cancels this j, so I have one single j inverse. And this is now completely in terms of C, okay? The only thing now that I want you to pay attention. This B bar, does that depend on X now? No, it's only dependent on C. That's it. Are these N's dependent on X? No, they're dependent on C. What is the only thing here you see here that depends on the coordinates of the element? J. That J is the only one, and in this case doesn't even depend on the coordinates. It's actually L over 2. But is the only thing that's going to have that information. P is just the forces. It's a given quantity, yeah. So I've made everything go from -1 to 1. The shape functions are the same. The derivatives of the shape functions are the same.
P is independent of that integral?
Which one?
Like the force vector is independent of the...
This one here it is.
Yeah.
This P is just the forces you apply. I'll give you an example that may help illustrate that.
Because like if you went to like, let's say like cylindrical coordinates with like the Jacobian, you wouldn't have to change P, or you would, right?
Well, let's stick to a bar for now, because going to cylindrical coordinate system, we're talking about something else now. But for a straight bar, which is what we're talking about, if I apply a force of 4 pounds or 5 pounds in the next node, doesn't matter. It's the same force I'm applying. Okay? All right, so Jacobian J, so that's called Jacobian, by the way. And I put subscript E because that's the only thing that depends on the element. Okay? Let's calculate these things really quickly. So B transpose, we came to a conclusion that the first term here is 1/2. That's -1/2. -1/2, 1/2. J was L over E over 2. I substituted everything here. Okay? I carried all the operations. You can see very quickly that none of this depends on deep C. None of these things. So that goes outside the integral. If EA is constant, of course, element to element, take it outside. And the integral from -1 to 1, that gives you 2. 2 times 2 is 4. 1 over 4 is 1. I get this. Isn't that what we got for before so many different times? Using the first lecture of this course also had 1 minus 1 minus 1, 1. And then later on, we derived it using weak form Galerkin. Then we derived it using finite elements. We keep getting this 1 minus 1 minus 1, 1. Okay? So that's an example. Let's move to the next example. Quadratic. Let's go back to this example. This example that was kind of painful because every element had, like this node was on the left, not in the center. This node was all the way to the right for the second element. And also this element was different size from that element. So that's a good example to do because it will show you then the number of calculations you have to do is a minimum, very little. Write the element code number 0, 1, 2, and then 2, 3, 4 for the second element. Okay, same process we've discussed. So for the quadratic bar, I have this integral here. Again, goes from xi to xj. I also have, this is b, bold b. We call it bold b times d. And this is not something I want. I want to substitute x in terms of the natural coordinate system. Same steps. So instead of dx, I want to have dxc. Instead of x, I want to have x as a function of c inside of these things. Okay, so this is what I really want. Then we went through the steps to substitute that in there. We calculated the dx dip c, dx as a function, and I'm repeating this again, but I'm doing it on purpose because the first time I saw this, I think I had the same blank face, but I'm hoping the second time you don't have a blank face, you follow it, okay? And for those in the video, they can replay over and over and over, right? But dx dip c, and that's j, we call it j, dip c. And then now that I know dx, I know x, I can calculate what j is, which is dx dip c. So just take the derivative of this with respect to c, and so then have ni as a function of c, nj with respect to c, nk with respect to c. So that's your j right there. These calculations, you know these values. You can take that derivative, you agree? You can take that derivative. I can put this in matrix format again, so this we're going to be bar, bold bar, and these coordinates, I'll put them in a vector called x, bold x, okay? Now I can substitute this into this equation here at the bottom. I already converted dip x into j dip c. I already converted that one, at least, these integrations. And I also changed the limits of integration to go from -1 to 1 already. Okay, so I've done that step. And so now I take the derivative of the shape functions. I have to do that calculation, to be able to get b in there. And so I do that for each of them using the chain rule. And I already went over this, but I know n as a function of c, not as a function of x. So I cannot take this derivative explicitly. So to do that, I have to use this formula for chain rule. So dn dip c, dn dx, dx dip c. So dx cancels, and then you get that one over there. This one, again, is j. You already know that. So I can solve for this here. And so now I have the component, which is that one, that has to go inside here. And I can repeat that for nj and nk. Okay, they all have the same thing, j inverse, j inverse, j inverse. You follow it for quadratic element? Okay, excellent. And if I put this in here, right, and I put this in here and this here, you agree that j inverse kind of factors out? They all have j inverse, so they all factor out. Isn't that what we had defined as b bar? B bar. B bar is basically this guy's here. Okay? So that's b bar right there. B bar. So now I have b as a function of b bar, which does not depend on the element coordinates, just depends on c. That's it. And then j inverse, which this one does depend on the element coordinates. Okay? If I substitute this here, I'm done. I have b transpose j inverse, b transpose j inverse, and that's it. And one of these j's cancels out, so it gives you a single j inverse. Okay? There's a j sub e missing here. My intention was to show what depended on the element. And so j is the only thing that depends on e. Everything else is provided. And now remember, j is b bar x. Okay, that was discussed in the 2 slides ago here. J is basically this calculation here. Okay, for the linear element was L over 2, but for quadratic element it can be more complicated. Okay, so let's apply this. One more thing. Observations. So this is what I got. The observations are, the integral of any element goes from -1 to 1. Okay. The shape functions and the derivatives are the same for every single element. The Jacobian is the only thing that's going to depend on the coordinates. Okay, so let's apply this. You're going to see my Mathematica code. Okay. And if you want, I can send it to you if you're interested. So shape functions. I'm going to, instead of using c, I use p. Okay. I didn't want to use c because then I have to copy that symbol over and over. I want to keep it simple here. So isoparametric formulation, these are the shape functions that we defined earlier. No different. They're the same shape function we discussed earlier, and you can check it. That's for node I, node j, and node k. And you can check that it works. For example, this will go to 0 at p equals 1 and p equals 0. But it's 1 at p equals -1. You can check all these things. It's going to work out. I find the derivative. Don't I have to take derivatives of shape functions? And I put them in a vector called b bar. Remember that? Voila. That's your derivative. Let them do the work, Mathematica. Take the derivative of this set of shape functions, and it gave it to me. That's my b bar. That's b bar. That's, I see some blank faces, but that's this here. Right there. Do I have to do this for every single element? No, I'm done. That's the only thing I have to do. Right there. Okay? This, you store this information for that element because you know you're going to have to need it again. But that's, you're saving a lot of computational time by not having to do these calculations. Now I have to define the coordinates. Remember I had to define the vector x? Remember that? I had to define x, the vector x of the coordinates. So for element 1, it was the nodes go 0, x equals 1/3 of L, and then L. For element 2, it started at L and the middle node was about 3L, if you remember. Yeah? I don't want to show you the picture again. You guys will remember if you remember the example and you studied the example. So the Jacobian, if you remember, the Jacobian was simply b bar times x. So what I did in Mathematica, I calculated Jacobian. B bar times x element 1. So this b bar times x element 1 gives me Jacobian for element 1. For element 2, b bar times x element 2 is Jacobian number 2. Now, check this out. Jacobian 1 and Jacobian 2, these are the only thing that are different from one element to another. Everything else is the same. Shape functions, derivatives, integrals, minus 1 to 1. So let's look. For element 1, for stiffness matrix 1, I just did that calculation here in Mathematica. Transpose of b bar is this one. Dot b bar, which is that one. Then I have J inverse, so I divide it by J1. This symbol here is to select that value. You can check it out in Mathematica, but that's more to select the value of J1. I could have written this, what J1 is. J1 was in the previous line here, which is this. I was just trying to select this number, and that's how you do it in Mathematica. You put, when there's, basically, I'm just selecting that from the list, extracting that number. But you can also write that. And then the integral goes from minus 1 to 1. Check this out. Does b bar depend on x? On the coordinates? No. This only depends on c, and it's the same for every single element. J1 is the only thing that depends on the coordinates. And then I have the integrals. Does the integral limits change? No, it's the same for every single element, minus 1 to 1. For element 2, look at this. I just did copy and paste. What is the only thing I changed? Instead of J1, I made a J2. Is the integral the same? Limits? Yes. Minus 1 to 1, minus 1 to 1. Go ahead.
What is L?
I just put L here. Okay, so, yeah. I was trying to trick the integral in Mathematica. It didn't want to integrate it for me. I wanted to do a numerical integration because it's a very complicated integral to do. Right? And so I was trying to cancel L out so it will integrate it numerically for me, and then I put L in the front. I was trying to trick it just to get it to integrate it for me because it couldn't do it symbolically for whatever reason. Okay? But don't get hung up on those details. That's not what I want you to understand. The process, the implementation. You know, you're not going to be integrating this symbolically anyway. You're going to do it numerically. Okay? And also it's my fault for selecting a problem where it has a variable like L. I should have made it L equals 1 or L equals 2. You see what I'm saying? I should have made the modulus of this material steel and cross-section 1 inch squared. Just make it easy, right? I didn't do any of that. But because I put some variables, I had to integrate it numerically. That's why I did that trick. But good question. So I got a stiffness metric for element 1 and 2. Now let's calculate the number of operations I did here, just to check it out. Do I do this for a million elements? Say I have a million elements. I do that just once. You agree? B bar, just once? Yes. This one is not an operation really. This one you have to do for every single element, sure. That's not too hard. I know B bar and I know X element. That's just a dot product of the two. Then the integrate. Then integral. This is way less steps than what I did last week and when I was reminding you about this problem. Then I did the force vector here. Remember the element 1 didn't have any distributed force, only element 2. But I did it here. And when you go through that, very simple, you get the vector for the forces. Which, remember, it was giving us 0 here. Right? But it's not giving us 0 here because of the way we're doing it. Okay, now proceed and solve the system of equations. So basically assemble the system of equations. All right, let's start with a new example altogether. Just a new example that you've never seen. So we'll do an ODE, just a random, I don't know, I made it up this morning, this differential equation. Okay, so this differential equation, and I made one that had like Bessel functions, like the solution is a Bessel function. Okay, to prove my point. My point is that this is hard to solve. Even I don't know even how to solve this by hand. It's been many years since I took differential equations. But anyway, I don't know if you're a mathematician, you probably know how to solve it, okay? Anyway, that's a differential equation I chose. Has no this is not physics-based. Not physics-based at all. Actually, we can make it physics-based if we want to, but that was not my purpose. My purpose was to say, hey, can I use finite elements to solve it, right? And it's to drive a point home. That's really why I'm doing this. So that's a derivative. U is a variable of interest. U prime at 1 is 1, and then U2 is equal to 1 at the other boundary. Okay, so I have this ODE needs to be solved between x equals 1 and 2. That's really what we want to do. I solved it in Mathematica, and I don't know. I just plotted this. That's the solution. That's the exact solution right there. Okay, I had high concerns. I may not be able to get the solution right, but it worked out at the end. I cannot believe it. Okay. All right, so that was the solution. Step one, form the residual function, perform the weighted integral that goes from xi to xj, some random xi to xj basically. So you're developing the element formulation now. So I took that multiplied by v, the weight function, remember that? Okay. Share the continuity, so basically reduce the continuity requirements because I have two derivatives here. Share one with v, so integrate by parts. You guys know, you're an expert on how to do this now. All right. Then I did that. Plug it back in. This bottom one, minus v prime 3x u prime, that's here at the bottom, plus ux v plus 10v dx. And then I have these boundary terms. These are the boundary terms that I get. Okay. And I'll cover the boundary terms more. You're going to see I'm going to keep them alive for a little while because these ones have no physical meaning. Remember, this problem has no physical meaning. Normally it's a force, a heat flux, you know. Normally there's a meaning, but in this example there's no meaning. It's just an example, okay? We can make it into a meaningful problem, but I didn't. That was not my intention, okay? I call these Q's, okay, because here what I wanted to point out is that if what is not V is Q, I'm at a Q. What is not V, I'm at a Q. And what I wanted to point out, this V tells you what is an essential boundary condition, what is not natural boundary condition. Here V tells me that if I make this V into U, that whatever is specified on U is an essential boundary condition. Everything else here must be a natural boundary condition. So when I look here, I know that's essential, I know that's natural. Okay, very quickly I know that. Anyway, I can either keep writing this over and over here, or just make it to QK and QI and just carry it on as I go. Okay, I do it both ways just to maybe confuse you. I don't know. That might be one reason I do things. Okay, so I have the weak form here. Weak form here. Just a second. All right, so this is a weak form of the problem. I'll substitute U to be the approximation function, and that's my approximation function. Remember, is the basis function times the unknown nodal quantities Ui, Uj, and Uk. So all of this is substitute. This is what I want to substitute in there. I also have to take these derivatives of U prime. So I did it ahead of time to remember that I need to do that. I call this B bold, okay? And instead of selecting V to be Ni for the first equation, V to be Nj for the second equation, V to be Nk the third equation, because you have to do that for each basis function. I already taught you the trick. Just make V to be N transpose. Be done with it. Okay? And if you have a derivative, so like here I have V prime, you already know that the derivative of the shape function matrix is B. Right? Is B. So just call it B transpose. So anywhere you see V prime, I'll put it B transpose. Anywhere I see V, I'll make it N transpose. That's the goal here. Okay. So that's what I did. I made V prime to be B transpose, U prime to be B times D. U here is N U is N, V is N transpose, just like we discussed. But U is actually N times D. V is N transpose, and I keep this on the right-hand side, but now it becomes a vector, and you can check it that it works out. If you put Ni here for the first equation, Nj for the second equation, Nk for the second equation, third equation, you will see that you will get these three numbers. Or if we revert back, just revert back to what we had. This is what we had before. Okay? All right. Now, I'm not done yet, because right now this form is painful. I have two elements of different sizes. I have the middle node is somewhere else. It's not, well, no, actually in this example I made it center just to make it faster, but you get the idea. Okay, so I'll develop an isoparametric formulation for this to enable the limits of integration to go -1 to 1, to have the shape functions to be the same for every single element, and then the derivatives also will be the same for every single element. So going back here, just to remind you, x was that for a quadratic element. And this is what I have in bold times x. Okay, and then I have dx dip c, so I can substitute what this Jacobian, this dx is. I will have to calculate these things. And we realize here quickly that dx equals j times dip c, so that's that here. That's that here. I also noticed that from B transpose, remember, that's basically B bar divided by J. So B bar times 1 over J. Remember that? Okay. And also there, B, 1 over J, so that's J squared. These n's stay the same. This x, I know what this x is, don't I? That x is bold n times x. So just put it in there. Directly, right there. Okay. And on the right-hand side, dx is dip c j. I kind of left that there, just like that. Why not? Just leave it there. Okay. Any questions on this? I just derived the isoparametric formulation. I just did it in one step. Please don't fear to ask any questions. If you don't follow a step, let me know and we'll go back and review. But I think you can follow it because this B, right, this B is basically in the previous slide. This B is this B here, B bold, right? And so B bold, we already shown you that is B bar times 1 over J. We showed you that step. So all I did, I plugged it in there. Okay. Now this B bar is easy to calculate because it's basically this values here. Okay. This B bar is composed of this derivative, and this derivative in a matrix format. Okay. All right. Any questions? Okay. So now I'm ready to go to Mathematica. Let Mathematica do the work. I discretize the domain into two elements, element 1 and element 2. Element 1, I decided to make a different size from element 2, just for purpose of illustration. Element 1 has 3 nodes, quadratic element. Element 2 is also 3 nodes, quadratic element. I put the node in the middle, you know, just to make it easy for me, right? But for you, we can make it different if you want. For the homework, we can make it, I don't know, you choose it. I'll make it happen for you. All right. Shape functions are the same for every single person here. Every single element has the same shape function. I put them in a matrix so they can take the derivative of this at once So I get b bar. That's b bar, the derivative of this. By the way, I could have just chosen, since this is coded up, right, in Mathematica, for the previous example, I could have just left it there. But just to remind you that this have to be calculated, okay? The coordinates of the element. Element 1 has coordinates of 1, 1.125, and 1.25. X element 1. And X element 2 is 1.25, 1.625, and 2.0. Those are the coordinates. I just stored them there in a vector. So then the Jacobian, if you remember, is b bar times X element 1. So it gave me 0.125, and then b bar times X element 2 is 0.375. For this example, it came out very nicely. Okay. And the connectivity matrix is 1, 2, 3. So 1, 2, 3. And then for element 2 is 3, 4, 5. 3, 4, 5. Any questions on that? Again, I don't have to redo anything here above. That's already done forever. Okay? I don't know if you can see this or whether it's too small, but all I did is calculate this whole thing. For the stiffness matrix, I did it here. Okay? I just did it in one step. Transpose b bar, that's this one here, times b bar divided by j1 squared. You see this j1 squared there? Okay? So for element 1, plus the transpose of n times n, shape function n. And you see this here at the beginning, m1, okay? I was having some trouble with Mathematica, but the bottom line, I was trying to calculate this number, minus 3 times n times x. That's what I was trying to do. You can see it here, I did it here. n1 equals minus 3 times n times x. That's what I was doing there. But I was having some trouble, so I just selected from the list that value. And the rest is exactly what you see there. You can follow it at home. Integral from minus 1 to 1. Bam, done. Okay? So for K1, Mathematica told me is this. For Q1, the distributed forces, which is this guy here, is basically that guy. Oh, that's the distributed forces from this guy. But I can look at this now. Now I can evaluate for element 1. Let's look at that. Did I specify U prime? Let's go back to the problem. I specify U prime at 1, nowhere else. You agree? Yes?
Yes.
So if I look here, I specify U prime for node 1, for element 1. You agree? But I didn't specify U prime anywhere else. You agree? So for element 1, if U prime is 1, okay, and what is the value for node 1? What is the coordinate for node 1? 1. So 3 times 1 times 1 is 3. And I didn't specify any slopes anywhere else. So that's 3, 0, 0. So I have 3, 0, 0. Okay? Very simple. For element 2, I repeated it. Again, not many calculations to do at all. It was really quick. It gave me the value for K2, the matrix for K2. The integrals, again, go from minus 1 to 1. Again, I did the minus 3 times n times x for element 2 in the previous page, but I had to do it separately for whatever reason. And then I calculated the rest here very quickly. I did the distributed forces. For the distributed forces, I have that. For which are not forces. They may not be forces. I don't know what they are. There's something. Okay? This is not a solid mechanics problem. I just made up a differential equation. That was my goal. I don't specify any slopes for element 2. So these are zeros. Okay? Now I have for element 1, I have that. For element 2, I have that. For load vector, I have that. For load vector, I have that. For element 2, do the assembly process. You guys are an expert at this. You know why I left that empty. Why? It's symmetric. Okay, in this example, it's symmetric. I did the assembly here so you guys can see that, how I assembled it. I made this into a reaction force since I specify a value. If you remember in my problem, I made U2 to be 1, remember? u2 to be 1. So that's node 5. I made it 1. So because of that, I probably have some sort of reaction force. It probably doesn't even exist, right? I mean, that has no physical meaning. So I could have just made the whole thing unknown, like R. I don't know what it is. And even if I calculate it, I don't know what it means. The bottom line is, for this example, I was able to solve for U1, U2, U3, and U4 very quickly. And guess what? U exact and U finite elements. Okay? At the different nodes I was solving for. And the error was less than 0.1%. Less than 0.1%. Actually, I'm being very generous here. I was actually rounding things off to make it probably worse. But it's really, really nice. 0.1%. And I use the integration within Mathematica. It's n integrate in Mathematica. Now, do you have an n integrate function in in finite element code? Yes, you do. What is that? So that's the next discussion now. How to integrate. Okay? So the next discussion today now is numerical integration. Okay? How to integrate in, you may have learned in school that you notice, somebody here noticed the integrals go, why you're going from -1 to 1? That was a question I thought I got a couple of times now. There's a reason. Numerical integration. There's a technique called Gaussian quadrature that works for these integrals that go from -1 to 1. They're perfectly suited for that. Okay. All right. So there's other techniques called the midpoint rule, trapezoidal rule, and Simpson's rule. Okay. You can that's covering numerical methods, some other classes. In essence, when you integrate with numerical methods, all you're doing is calculating the area under the curve. Right? But this other technique called Gaussian quadrature, which is what is used in finite elements, right here. Okay. Even in my PhD code, my element that I use that connects with Abaqus is using this technique, Gauss quadrature. Okay. It's very powerful. Very powerful. The way it works, you have some integral that goes from x1 to x2, but you have to convert it to -1 to 1 to be able to use this. Okay. And how it works is that you'll sample the quantity phi, okay, at some values, and I'll give you a table that gives you those values. And they will come with some weights, okay, some values for weights. So W1 times phi plus W2 phi at this location. And if you have 1 point, you will use this. If you use 2 points, you use that. The more points you use, the more accurate it gets, okay? And so that way, you're integrating in actually just using this technique, sampling. You're sampling the domain. Yes, there's a question on there.
The W quadrature weight, is that the same as a weight function from the Quadratic method?
No. The question is, are these quadrature weights the same thing as the weights from Quadratic method? No. Just forget it. This is just purely mathematical. This part of the teaching that we're doing now, purely mathematical. Nothing to do with weak formularity, nothing to do with weight functions, none of that. This is purely mathematical. How to integrate something that goes from -1 to 1. That's the goal here. We're not discussing anything else. Excellent question. The quadrature points can be found in this table. For 1 point quadrature point, you'll evaluate the phi function as 0, and the weight function is 2, the one that goes ahead. For 2 points, will be these values, and the weight function is 1. And this is accurate exactly to this polynomial function. So if I have a linear polynomial, it will integrate that exactly. If I have a cubic polynomial with 2 sampling points, I get the exact value of that integral. Isn't amazing? Okay. With 3 points, I get up to a quintic polynomial to be integrated exactly. Okay. It's a very powerful method. Let's do an example. Let's say I want to integrate from 0 to pi sine x dx equals 2. I'll use, hey, why not? Why not use what we learned, right? So we'll transform the integral from -1 to 1. You guys already know the shape functions for ni and nj. Xi is 0 and xj is pi, so then xc is pi, 1 plus c divided by 2. Dx dip c, I have to change the dx to dip c. So dx dip c is dx dip c dx dip c. And that's basically the root of this with respect to c, and that's 1/2, so I have pi half dip c. So I converted dx into pi half dip c. And then for x, I substituted what x is in terms of c, so pi 1 plus c divided by 2. I put that inside where the x was. Okay, and my limits of integration go from -1 to 1. Any questions on that? Yeah? Straightforward, right? It's exactly what I did earlier. I'm doing it for a simple example, like extremely simple example. But it's the same thing we're doing earlier in the previous half of the course, lecture. Okay? Okay, I'll plug this in here. Oh, sorry, I have this. This is my new phi. My phi, I only use 2-point quadrature. Okay? So for 2-point, the weights are 1. You can see here, it's given here. The weights are 1, and that goes with this number, and then the weight is 1, and that goes with that number. That's basically 1 over square root of 3, in essence. Okay, I did that. I evaluated this at c equals -1 over square root of 3, this whole thing, times 1, the weight function 1, the weight quadrature point 1, plus evaluated that at c equals 1 over square root of 3, all this, times the function, the quadrature 1, and I get a value of 1.94, which is pretty close to 2.0. Now, somebody here could say, well, that's off. That's significant. Well, come on. I went from 0 to pi. Your element size is huge, right? We're looking at huge size. But if I wanted to get it better, I could have done it, right? I would have chosen a smaller limit. Okay? There's a question.
So how do you decide how many points you need?
Typically, the question for the video is how do I decide how many points I need? And the answer to that question is I'll give you an example to go through that, but usually 2 points does very well. And Abaqus typically uses 2 points.
For every function?
It usually uses 2 points for almost everything. It does very well, really well. I'll cover that in a second. How to decide. Another example, I did another example, a quadratic equation. I took a quadratic polynomial, integrated that. It's actually 1/3 the solution to that if you figure it out. I did it again with basically I took this, evaluated this at the c values in that table with a weight of 1 for each of them, and I got 0.333 exact. Okay, why does it work? I'm not going to cover this here. But if you want to learn how does it work, I provide that in this slide here. For n equals 1, I show you how to derive that. And for n equals 2. Okay? And I show you how this person derived it, Gauss quadrature. Okay? I sometimes cover it, but I feel like it's not unnecessary right now. You can go home. You can follow. It's very simple how this was derived. So for now, just use the table. Sorry, it's kind of stuck here. You use the table, and if you want to learn where it came from, and you want to learn, come to me after the class, and I'll guide you step by step. It's very simple. Well, I don't know. Whoever invented this, great idea. It's what's used in Abaqus and Nastran and all these codes. So it's great. I mean, I'm impressed with all this Feynman stuff. It's unbelievable. I feel privileged to teach it. It's unbelievable. For a linear element, your shape functions are linear. B is constant. Do you agree? Because I'm taking the derivatives of shape functions, so I get constant. So constant times constant is constant. So usually 1 point will be exact for that. I'm trying to answer the question here. If n is quadratic, the shape function is quadratic, so I have a quadratic element. B, since I'm taking a derivative of quadratic, I get linear, right, for B. So linear times linear gives you a quadratic function. So usually 2-point gives you an exact solution, exact integral to that. If I have a cubic for n, then a 3-point rule is better. Okay. So I could have integrated this problem with a middle node right in the center. And I did that for this example. For an element that goes from 0 to LE with a center node. And when you integrate it, the exact solution is given here. Okay. Just for the kicks, just to see if it works, the Gaussian integration, I multiplied this in Mathematica, multiplied it, and this is my new phi. All this is my phi. All this. I evaluated this phi at one of the Gaussian quadrature points, and I put the weight of 1, plus I did a 2-point rule, so n equals 2, plus the second psi times the weight of 1. And I added it up, and guess what? I didn't want to show it because it was exact. It was the same thing I got in the previous page. Okay? If I decide I want to use n equals 1 to see what happens. So say I want to use n equals 1, which is here. I only have 1 point, so C0 is where you evaluate this. And then you have a 2.0 for the weight. If you do this multiplication, you actually get this strange thing where you have 1, 0 minus 1, 0, 0, 0, minus 1, 0, 1. Well, that's not good news because now my middle node is not contributing to anything. Okay? So this element is actually unstable. This element is not a good element with this n equals 1. So using less integration points can also hurt you sometimes. And there will be cases that's actually helpful. And we'll cover that maybe in the next lecture, where reduced integration is actually more accurate than full integration. So what I did earlier with n equals 2 is full integration. I get the exact solution. With n equals 1, which is reduced integration, I want to use just 1 point instead of 2 points. Here, it hurts you. You get, on stable element, I have this middle node is doing nothing. If I calculate the strain energy for this element, I get this just the contribution of the first node and the last node. The middle node is like hanging out there. I don't know what it's doing, actually. I don't even know how to even solve for it. Okay? And so, the point I want to make is that reduced integration can, using less integration points, in some cases can hurt you. You will see later on that it actually can help you in some cases also. All right. So, that's my last note. Right now, we're going to take a 4-minute break. We're going to attempt to do something we've never done here before. And so for now, the lecture concludes, my part concludes, and I will start something that we have not attempted before. So if this does not work out, we will attempt to try it next time, okay? All right, just come back in 4 or 5 minutes.